Ladies and gentlemen, today, I have the pleasure of discussing a seemingly simple yet profoundly impactful invention, barbed wire. This ubiquitous material has played a pivotal role in agriculture, security, and even warfare. Although barbed wire might appear straightforward, its engineering and physics reveal a fascinating intersection of material science, mechanical engineering, and applied physics. The invention of barbed wire in the late 19th century stands as a watershed moment in the history of land management and fencing technology. Prior to its introduction, the task of enclosing large tracts of land was a labor-intensive and financially burdensome endeavor. Farmers and landowners resorted to various methods, including the use of stone walls, wooden rails, or natural barriers, to delineate their property boundaries and protect their crops or livestock. However, these traditional fencing methods were fraught with limitations, often requiring significant manpower and resources to construct and maintain. In 1874, Joseph Glyden, an American farmer from DeKalb, Illinois, changed the landscape of land fencing forever with his revolutionary invention of modern barbed wire. Glyden's design represented a quantum leap in fencing technology, offering a practical and cost-effective solution to the challenges of land enclosure. At the heart of Glyden's invention lay a simple yet ingenious concept: twisted strands of wire adorned with sharp barbs at regular intervals. This design innovation marked a departure from earlier attempts at barbed fencing, which had lacked the durability and efficiency necessary for widespread adoption. Glyden's barbed wire design addressed several key shortcomings of previous fencing methods. By utilizing twisted wire strands, Glyden achieved a balance of strength and flexibility that was previously unattainable. This structural integrity allowed for the creation of fences that could withstand the rigors of agricultural use, including the pressure exerted by livestock and the forces of nature. Moreover, the addition of sharp barbs along the length of the wire served as a potent deterrent against unauthorized entry, effectively discouraging both humans and animals from attempting to breach the fence. One of the most significant advantages of Glyden's barbed wire design was its ease of installation. Unlike traditional fencing methods, which often required extensive labor and specialized skills, barbed wire fences could be erected quickly and efficiently by individuals with minimal training. This accessibility democratized the process of land enclosure, enabling farmers and landowners of all backgrounds to establish boundaries and protect their property with relative ease. From an engineering perspective, Glyden's barbed wire represented a triumph of simplicity and efficiency. The twisted wire strands provided the necessary tensile strength to support the fence structure, while the sharp barbs served as effective deterrents against unwanted intrusions. The choice of materials, predominantly steel wire, offered a balance of durability and affordability, making barbed wire an accessible solution for farmers and landowners across the country. The invention of barbed wire by Joseph Glyden in the late 19th century heralded a new era in land management and fencing technology. Through a combination of innovative design and practical engineering, Glyden revolutionized the way in which land was enclosed and protected, providing a cost-effective solution that remains in use to this day. Glyden's legacy serves as a testament to the power of human ingenuity to overcome challenges and improve upon existing methods, ultimately shaping the course of history. The engineering brilliance encapsulated within barbed wire is a testament to the power of simplicity and efficiency. Joseph Glyden's stroke of genius was to conceive a design that married these two principles seamlessly. By ingeniously twisting two strands of wire together, he birthed a structure that boasted remarkable strength and flexibility. This structural integrity was further enhanced by the incorporation of barbs, crafted from short pieces of wire meticulously twisted around the main strands. These barbs not only served as a formidable deterrent to potential intruders, but also contributed to the overall robustness of the fence. What's truly remarkable is that Glyden achieved this feat without significantly inflating material costs. thereby democratizing the benefits of effective fencing solutions. Delving deeper into the mechanics of barbed wire, one uncovers a symphony of engineering marvels orchestrated to perfection. The intertwining of two wire strands creates a dynamic equilibrium, distributing stress evenly along the length of the fence. This uniform distribution of force is pivotal in safeguarding the fence against structural weaknesses, ensuring its resilience against external pressures. Furthermore, the twisted configuration imbues the wire with a remarkable degree of flexibility, allowing it to yield under duress without sacrificing its overall integrity. This flexibility is critical in environments characterized by fluctuating temperatures, soil conditions, or animal activity, where rigid structures would succumb to the relentless forces of nature. The inclusion of barbs, those menacing protrusions adorning the wire, serves as both a deterrent and a reinforcement mechanism. These sharp appendages, crafted from short segments of wire, are strategically positioned along the length of the fence to dissuade any attempts at unauthorized entry. However, their significance transcends mere deterrence. They play a pivotal role in fortifying the fence against external threats. When pressure is applied to the wire, whether by the weight of livestock or the elements themselves, the barbs serve as anchor points, distributing the force and minimizing the risk of structural failure. Thus, in addition to their primary function as deterrents, the barbs emerge as unsung heroes, silently bolstering the fence's defenses against unforeseen challenges. In the realm of materials science, barbed wire stands as a testament to the enduring supremacy of steel. The choice of steel as the primary material for barbed wire is no accident. It is a deliberate nod to its exceptional tensile strength, durability, and resilience. Steel's inherent properties make it uniquely suited for the rigors of outdoor applications, where exposure to moisture, temperature fluctuations, and physical stress is the norm rather than the exception. Moreover, the galvanization of steel wire with a zinc coating serves as a bulwark against the corrosive forces of rust and decay, ensuring that the fence remains steadfast in the face of adversity for years to come. In essence, the engineering and physics behind barbed wire encapsulate a symphony of innovation, ingenuity, and pragmatism. From its inception as a humble solution to the challenges of agricultural fencing to its widespread adoption in security perimeters and military installations, barbed wire stands as a testament to humanity's indomitable spirit of problem-solving. As we gaze upon the humble strands of wire adorned with menacing barbs, let us not only marvel at their simplicity but also appreciate the profound depths of engineering excellence that lie beneath the surface. The primary material employed in the fabrication of barbed wire is steel, meticulously chosen for its exceptional mechanical properties, such as tensile strength, durability, and resilience against environmental degradation. Steel, renowned for its robustness, provides the necessary structural integrity to withstand various stresses encountered in fencing applications. The selection of steel underscores the importance of materials engineering in ensuring the longevity and effectiveness of barbed wire as a fencing solution. To further enhance its corrosion resistance and longevity, the steel wire undergoes a galvanization process. This involves coating the wire with zinc, a sacrificial anode, which acts as a protective barrier against rust and corrosion. Galvanization not only shields the underlying steel from environmental elements but also ensures the continuity of the wire's physical properties over an extended period. This application of corrosion science demonstrates a strategic approach to materials selection and surface treatment in engineering design. The manufacturing process of barbed wire entails a series of precise mechanical and metallurgical procedures aimed at achieving the desired wire properties. Wire drawing, a fundamental process in metalworking, involves pulling steel rods through progressively smaller dies to reduce their diameter and increase their length. This process imparts work hardening, wherein the metal's crystalline structure is altered, resulting in improved mechanical properties, such as strength and hardness. Wire drawing exemplifies the synergy between mechanical engineering and materials science in optimizing material performance through controlled deformation processes. Once the steel wire is drawn to the requisite dimensions, it undergoes further processing to impart the distinctive characteristics of barbed wire. The drawn wire is twisted into pairs, a manufacturing technique that enhances the wire's flexibility and resilience to bending stresses. This twisting process not only imparts mechanical strength but also facilitates the integration of barbs into the wire structure. The precise manipulation of wire geometry highlights the importance of geometric design considerations in engineering applications, where even subtle alterations can significantly influence product performance. Adding barbs to the twisted wire involves specialized machinery designed to create sharp protrusions at regular intervals along the wire length. These barbs serve as deterrents, increasing the effectiveness of the fence by inflicting pain and resistance upon contact. The engineering behind barb formation encompasses considerations of geometry, force distribution, and manufacturing tolerances to ensure uniformity and consistency in barb dimensions. This meticulous attention to detail underscores the interdisciplinary nature of engineering, where mechanical, materials, and manufacturing expertise converge to realize innovative solutions. In essence, the engineering and physics principles underpinning the design and manufacture of barbed wire exemplify the ingenuity and precision inherent in modern engineering practice. From materials selection and surface treatment to manufacturing processes and geometric design, each aspect of barbed wire production reflects a synthesis of scientific knowledge and practical application. As we continue to advance in materials science and engineering technology, the legacy of barbed wire serves as a testament to the enduring impact of interdisciplinary collaboration and innovation in shaping the world around us. The physics behind the functionality of barbed wire delves deeply into the intrinsic properties of its primary material, steel. Steel possesses remarkable tensile strength, a fundamental property crucial for the wire's effectiveness as a barrier. Tensile strength refers to a material's ability to withstand pulling forces without yielding or breaking. In the context of barbed wire, this means that even under immense tension, such as that exerted by livestock or the forces of nature, the wire remains intact and capable of maintaining its structural integrity. This property is particularly essential for fences spanning large distances, where the cumulative stress can be considerable. Moreover, steel's high tensile strength ensures that the wire can endure extreme weather conditions, including strong winds and heavy snow loads, without succumbing to deformation or failure. By leveraging the inherent strength of steel, engineers have crafted a fencing solution that can withstand the rigors of agricultural and security applications with resilience and durability. The mechanical engineering principles underlying barbed wire's design further reinforce its robustness and effectiveness. One of the key design elements is the twisted pair structure, which imparts both strength and flexibility to the wire. Through the process of twisting two strands of wire together, engineers create a composite structure that distributes stress evenly along its length. This distribution of stress helps prevent localized failure points, ensuring that the wire can withstand significant tension without compromising its integrity. Additionally, the twisted pair design enhances the wire's flexibility, allowing it to adapt to uneven terrain and absorb dynamic loads, such as impacts from animals or external forces. This combination of strength and flexibility is essential for ensuring that the fence remains functional and secure even in challenging environments. The barbs, strategically spaced along the wire, serve as a deterrent against unauthorized access while also reinforcing the fence's structural integrity. These sharp protrusions create points of high pressure upon contact, effectively dissuading animals or intruders from attempting to breach the barrier. From a physics perspective, the concentration of force at the barb's tips amplifies the sensation of pain or discomfort, discouraging further interaction with the fence. Furthermore, The spacing and orientation of the bulbs are carefully optimized to balance deterrence with structural stability. Too close together, and the bulbs may weaken the wire, compromising its ability to withstand tension. Too far apart, and the fence may become less effective at deterring intrusions. By meticulously engineering the placement and design of the bulbs, engineers ensure that the fence maintains its dual function as a physical barrier and a psychological deterrent. The engineering and physics behind barbed wire epitomize the ingenuity and innovation of human problem solving. By leveraging the material properties of steel and applying principles of mechanical engineering, designers have created a fencing solution that is both robust and versatile. From withstanding the forces of nature to deterring unwanted intrusions, barbed wire exemplifies the intersection of science, engineering, and practical application. As we continue to advance our understanding of materials and mechanics, the lessons learned from barbed wire's design and functionality will undoubtedly inspire new innovations in the field of security and beyond. The mechanical engineering principles underpinning the design of barbed wire are as intricate as they are ingenious. At the heart of its effectiveness lies a careful balance between structural integrity and deterrent capability. The twisted pay design, a hallmark of barbed wire's construction, serves multiple functions. Not only does it distribute stress evenly along the wire, mitigating the risk of localized failure points, but it also confers a crucial elasticity to the fence. This elasticity allows the wire to flex and absorb energy from impacts, such as those generated by animals pushing against the fence. Moreover, the strategic placement of barbs is a testament to the meticulous engineering behind this seemingly simple invention. Each barb serves as a sharp deterrent, discouraging animals or humans from attempting to breach the fence. Yet, their spacing and orientation are meticulously calculated to strike a delicate balance. Too close together, and the bulbs risk weakening the wire's overall structure, compromising its effectiveness as a barrier. Conversely, if spaced too far apart, they may fail to adequately deter potential intruders. Engineers have thus settled on a spacing of 4 to 5 inches, a compromise that ensures both deterrence and structural integrity are upheld. Furthermore, the design of barbed wire exemplifies the marriage of physics and engineering. The sharpness of the bulbs concentrates force into small areas upon contact, dramatically increasing the pressure exerted. This principle, rooted in the physics of pressure, results in a painful or injurious experience for anything attempting to breach the fence. It's a powerful deterrent mechanism that capitalizes on the physical response of animals and humans to pain. Additionally, the elasticity of the wire plays a crucial role in dissipating energy from impacts. When subjected to forces such as those generated by a large animal colliding with the fence, the wire can deform temporarily, absorbing and dispersing the energy across its length. This not only reduces the likelihood of damage to the fence but also helps to minimize injury to the intruding animal or individual. In essence, the engineering and physics behind barbed wire are a testament to human ingenuity in solving complex problems with elegant solutions. From the careful consideration of material properties to the strategic placement of deterrent features, every aspect of its design reflects a deep understanding of both mechanical principles and the behavior of living organisms. As we continue to refine and innovate upon this timeless invention, it serves as a reminder of the remarkable synergy between science and engineering in shaping our world. Installation of barbed wire is a precise endeavor that demands meticulous attention to detail. At the heart of this process lies the critical task of tensioning. Tensioning is not merely about pulling the wire tight, it's a delicate balance between maintaining structural integrity and ensuring effective deterrence. Too little tension, and the wire sags, compromising the fence's ability to contain livestock or deter intruders. Conversely, excessive tension risks structural failure, with the wire snapping under the strain or posts buckling under the pressure. Engineers approach tensioning with a blend of art and science, employing specialized tools and techniques honed through years of experience. Fence stretchers are indispensable instruments in the tensioning process. These devices allow for controlled and gradual stretching of the wire, ensuring uniform tension along the entire length of the fence. By spreading the tensioning force over a larger area, fence stretchers minimize the risk of localized stress concentrations that could weaken the wire or damage the support posts. Moreover, they provide engineers with precise control over the amount of tension applied, enabling them to fine-tune the fence's performance according to specific requirements. Tension gauges are another essential tool in the engineer's arsenal. These devices measure the tension in the wire with precision, allowing engineers to verify that the desired level of tension has been achieved. By quantifying tension in terms of pounds or kilograms, tension gauges provide objective feedback, guiding engineers in their decision-making process. This quantitative approach helps ensure consistency across multiple sections of the fence, minimizing variations in tension that could compromise its overall effectiveness. However, tensioning is not solely about achieving a specific level of force. It also involves understanding the material properties of the wire and its response to external factors. Steel wire, while incredibly strong, has its limits. Engineers must account for factors such as material fatigue, thermal expansion and contraction, and environmental conditions when tensioning the wire. By considering these factors, engineers can optimize the tensioning process, maximizing the fence's lifespan and performance. Moreover, the tensioning process is iterative, requiring ongoing monitoring and adjustment. As environmental conditions change and the wire undergoes wear and tear, tension levels may need to be recalibrated. Engineers rely on their expertise and intuition to anticipate these changes, preemptively adjusting tension as needed to maintain the fence's effectiveness. This proactive approach not only prolongs the life of the fence but also minimizes the risk of costly repairs or replacements down the line. In essence, tensioning is a dynamic process that goes beyond mere mechanical manipulation. It embodies the principles of material science, structural engineering, and applied physics, requiring a deep understanding of how forces interact within the system. By mastering the art of tensioning, engineers ensure that barbed wire fences not only fulfill their practical function but also withstand the test of time in the face of ever-changing environmental and operational challenges. The physics behind the deterrence capability of barbed wire delves into fundamental principles of pressure and pain response. When an object, be it an animal's skin or a trespasser's hand, encounters the sharp barbs, the resulting interaction initiates a cascade of physical forces. These barbs, meticulously designed to be sharp and pointed, concentrate the force exerted by the contact onto a minute area. This concentration of force magnifies the pressure exerted on the object, often causing pain or injury upon contact. The immediate physical feedback of this encounter serves as a powerful deterrent, discouraging further attempts to breach the barrier. Beyond the purely physical aspects, barbed wire's deterrent effect is augmented by its visual appearance. The sharp, menacing presence of the barbs creates a visual signal of danger that is instinctively recognized by both humans and animals alike. This visual cue triggers a psychological response, evoking feelings of caution and apprehension in potential intruders. The combination of these physical and psychological barriers forms a formidable defense, dissuading many would-be trespassers from attempting to breach the perimeter. Barbed wire's effectiveness as a deterrent is further amplified when considering the principles of material science and mechanical engineering that govern its design and construction. The selection of materials, particularly high-strength steel, ensures that the wire can withstand significant tension without breaking or deforming. This resilience is critical for maintaining the integrity of the fence over time, especially in the face of environmental factors such as wind, precipitation, and temperature fluctuations. Moreover, the mechanical properties of barbed wire, including its elasticity and flexibility, play a crucial role in its effectiveness as a barrier. These properties allow the wire to absorb and dissipate energy from external forces, such as impacts from animals or attempts at tampering. By distributing stress evenly along its length, the wire minimizes the risk of localized failure points, ensuring that the fence remains robust and secure. In essence, the engineering and physics behind barbed wire converge to create a multifaceted deterrent system that combines physical strength, psychological deterrence, and material resilience. Through careful consideration of these principles, barbed wire has established itself as a versatile and effective fencing solution, serving a wide range of applications from agricultural enclosures to high-security perimeters. In the realm of barbed wire innovation, modern engineering has propelled the evolution of its design and functionality. One notable advancement is the development of high-tensile barbed wire, representing a leap forward in material science and manufacturing techniques. Unlike traditional barbed wire, high-tensile variants utilize advanced steel alloys that exhibit superior tensile strength and resilience. These alloys undergo precise metallurgical processes, including heat treatment and alloying, to enhance their mechanical properties. The result is a wire that can withstand greater tension and environmental stresses without compromising its structural integrity. Engineers meticulously optimize the alloy composition and manufacturing parameters to achieve the desired balance between strength, flexibility, and corrosion resistance. This meticulous approach ensures that high-tensile barbed wire meets the demanding requirements of modern applications, from agricultural fencing to security perimeters. Furthermore, the advent of coated barbed wire represents a significant breakthrough in enhancing durability and longevity, particularly in harsh environmental conditions. Coated wire incorporates additional layers of protective materials, such as polymer coatings or corrosion-resistant alloys, to shield the underlying steel from corrosion, abrasion, and UV degradation. The engineering behind coated barbed wire involves careful consideration of material selection, coating thickness, and application methods to maximize performance and durability. Polymer coatings, for instance, offer excellent resistance to moisture and chemical exposure, prolonging the wire's service life in corrosive environments. Similarly, corrosion-resistant alloys, such as stainless steel or aluminum zinc alloys, provide inherent protection against rust and oxidation. Engineers leverage advanced coating technologies, such as electroplating, hot dipping, or powder coating, to apply these protective layers uniformly and securely to the wire surface. This ensures robust corrosion protection while maintaining the wire's mechanical properties and aesthetic appeal. Moreover, modern engineering has facilitated innovations in barbed wire installation techniques, optimizing efficiency and reliability. One notable advancement is the development of automated tensioning systems, which streamline the installation process and ensure consistent tension across the entire fence line. These systems employ sophisticated mechanisms, such as hydraulic or pneumatic actuators, to apply precise tension to the wire while minimizing human effort and error. Engineers leverage principles of mechanical design and control theory to develop tensioning systems that can accommodate varying terrain, temperature fluctuations, and load conditions. Additionally, advanced anchoring methods, such as driven or helical anchors, offer secure attachment points for the wire, enhancing stability and longevity. These engineering innovations in installation techniques not only expedite the fencing process but also contribute to the overall reliability and effectiveness of barbed wire fences in diverse applications. The field of barbed wire engineering continues to evolve, driven by a relentless pursuit of innovation and optimization. From high-tensile alloys to advanced coating technologies to automated installation systems, modern engineering has expanded the capabilities and performance of barbed wire in agricultural, security, and industrial applications. By leveraging principles of material science, mechanical engineering, and automation, engineers continue to push the boundaries of what is possible, ensuring that barbed wire remains a versatile and effective solution for perimeter security, livestock management, and land delineation. Barbed wire's applications transcend its traditional role in agriculture, finding extensive use in security perimeters for various installations, including properties, prisons, and military facilities. In these contexts, its effectiveness as a deterrent is amplified when integrated with complementary security measures. Engineers meticulously design these systems to ensure seamless integration and optimal performance. Consider, for instance, the combination of barbed wire with electric fences. The engineering challenge lies in synchronizing the operation of both systems to maximize security while minimizing false alarms or malfunctions. This requires a deep understanding of electrical circuitry, impedance matching, and voltage regulation. Moreover, the placement of barbed wire atop electric fences necessitates careful consideration of insulation and grounding to prevent unintended shocks and ensure safety. Surveillance systems play a pivotal role in modern security installations, augmenting the deterrent effect of physical barriers like barbed wire. Engineers leverage principles of optics, signal processing, and data transmission to design surveillance cameras and sensors that seamlessly integrate with the fencing infrastructure. By strategically positioning these sensors along the perimeter, they can detect and alert security personnel to any breaches or suspicious activity, enhancing overall situational awareness and response capabilities. The evolution of fencing materials, spurred by advances in engineering and physics, has led to the development of innovative alternatives to traditional barbed wire. Razor wire and the concertina wire, for example, build upon the same principles of pressure, pain response, and structural integrity to provide enhanced security. Razor wire features sharp, razor-like blades affixed to a central wire, maximizing the deterrent effect and making it even more difficult to breach. Concertina wire, on the other hand, consists of multiple coils of barbed wire, creating a formidable obstacle that is both flexible and impenetrable. The design and deployment of these advanced fencing materials require a nuanced understanding of material science, mechanical engineering, and human physiology. Engineers must balance factors such as tensile strength, sharpness, and spacing of the barbs to optimize deterrence while ensuring safety and compliance with regulations. Furthermore, they must consider environmental factors such as corrosion resistance and weather durability to maintain effectiveness over time. In essence, the applications of barbed wire and its derivatives in security contexts highlight the intricate interplay between engineering and physics, from the integration of multiple security systems to the development of advanced fencing materials. Engineers continue to push the boundaries of innovation to safeguard critical infrastructure and protect lives. In conclusion, barbed wire stands as a testament to the profound impact that simple yet ingenious engineering can have on society. Its development represents a harmonious blend of material science, mechanical engineering, and applied physics. At its core, barbed wire embodies the principles of material selection and manipulation, with steel chosen for its exceptional tensile strength, durability, and resistance to environmental degradation. This choice is not arbitrary, rather, it reflects a deep understanding of the physical properties required for a successful fencing solution. Moreover, the manufacturing processes involved in producing barbed wire exemplify the marriage of engineering precision and industrial innovation. The transformation of raw steel into intricately twisted strands, each punctuated by sharp barbs, is a testament to human ingenuity. Wire drawing techniques, which involve progressively reducing the diameter of steel rods through mechanical force, enhance the wire's strength and resilience. Meanwhile, the addition of zinc coatings through galvanization serves as a barrier against corrosion, ensuring the longevity of the fencing material even in the face of harsh environmental conditions. The mechanical engineering principles underlying barbed wire's design are equally remarkable. The twisted pair configuration of the wire strands distributes stress uniformly, minimizing the risk of localized failure and enhancing the overall structural integrity of the fence. This design not only confers strength but also imbues the wire with a degree of flexibility, enabling it to absorb and dissipate energy from external forces such as wind or animal impact. Furthermore, the strategic placement of barbs along the wire serves to amplify its deterrent effect, leveraging principles of pressure and pain response to dissuade potential intruders. Tensioning, a critical aspect of barbed wire installation, embodies the principles of mechanical equilibrium and material elasticity. Achieving the optimal tension ensures that the wire remains taut and effective over time, resisting sagging or deformation. Engineers employ sophisticated tools and techniques, such as fence stretchers and tension gauges, to precisely control the degree of tension applied to the wire. This meticulous attention to detail reflects a deep understanding of the underlying physics governing structural stability and performance. Ultimately, the lessons gleaned from the engineering and physics behind barbed wire extend far beyond its immediate applications. They serve as a timeless reminder of the importance of simplicity, efficiency, and thoughtful design in addressing complex societal challenges. As we confront ever-evolving threats and opportunities, the enduring legacy of barbed wire encourages us to embrace innovation while remaining grounded in the fundamental principles that underpin our technological achievements. Thank you.